It's already 2 p.m. I think.
Shall we begin?
We are live. Let's see. I want to see it here.
We are now live.
And but it doesn't show the camera. That's the problem. That's not something like. What should we do? While introducing the mission, I could just say can you pin this actually? Can you make it like pins for everyone? I think there's that option. Oh, pins for everyone. Okay.
Yeah, the camera started displaying.
Okay. We're just trying to be sure about YouTube. Okay. So should I actually close the window? Does no noise? Up to you. Is it distracting for you?
It's not distracting, but it's more for people back there. Hey, can you hear me talking back there, or is this too soft? No.
Also, yeah. Is the microphone turned off? I think so.
Oh,
yes.
you're saying this to broadcast over the speaker? Yeah, because that would just be
Yes,
pure
yes,
feedback,
yes,
right?
Yes. It's okay. Yes. I mean, I don't hear that stuff like that. It's not so far away. It's not so far away. So we have.
Oh gosh, because it's not playing my own audio back on my own computer to play here, right? So Zoom is treating it like it's consuming the audio instead of playing it here.
I'm not sure, but I think you need to turn on your mic and do that. So
It is. It's all on. Right, like this is picking up my voice and broadcasting it to the Zoom session.
okay, but I don't hear it on you. I mean, assuming you're setting the correct, it says microphone speakers, it's on. During YouTube, the sound is good. I should be hearing.
So it should be this guy speaking. Yeah.
That's Hassan.
Hassan. What?
Now we're playing another YouTube video.
I see.
I'm hearing from YouTube.
Yeah, so if I'm speaking here, you're hearing? Yeah, okay. No, but the problem is that it's not amplifying for the room, so the people on the back have it there.
Yeah, that's
No, they're here. It's fine. Can you hear? You cannot hear?
I can hear.
Okay, you speak louder then.
I mean, I can speak kind of loudly, but I don't know if I can keep this up for like an hour. Yeah, I can try. Okay, if it becomes a problem, then just let me know, yeah? But yeah. What's
I
that?
don't know. I cannot increase it.
Because ideally you would just have it pick up and amplify, right? Like a
Yes,
microphone.
yes, but it was working. It doesn't work now. I don't know why.
Okay. Should I try and stand more over here?
No, I think it's fine. And we're already on live stream. Let's start.
Okay, let's get started.
Okay, welcome everybody for today's software live seminar. So today we're proud of hosting Dr. Minesh Patel. He got his PhD from Zurich from software group actually, and it was about a year ago. And before that, he got his bachelor's both in physics and electrical engineering in UT Austin. And his PhD dissertation is mostly focusing on the reliability, security, and performance of computer systems in general. I believe it's not limited to memories anyway. He published several top tier papers, and he got a bunch of best paper awards from DSM 19 and Micro 20, and his dissertation was also awarded as a William Carter Dissertation Award in Dependability in DSM. And he also got an ETH doctoral medal, and he's in the ISCA Hall of Fame now. So Minesh will soon, I guess in the next year, will start as an assistant professor in Rutgers University. So welcome Minesh, and we're excited to hear about your talk, your research plans, everything.
Yeah, thanks for the introduction, Kirai. So yeah, so thanks to ETH and Safari for hosting me here to give this talk. So I'm going to be talking about DRAM scaling and how the outlook for that is in the future and what we might be able to do about it. So before I get started, one of my co-authors had an interesting idea. It's to talk about, oh, the remote stopped working. Okay, 1 second. Yeah, is to talk about, so what this talk will not be about, right? So this particular talk won't be about mechanisms to improve system level metrics such as performance and so forth. It won't be about theory or experiments or analysis of those experiments, right? So what it's actually going to be about is more of a reflection on how we build and use memory devices today, looking at what the indirect costs are of current design practices and essentially the status quo of how memory is built and integrated into systems, and also improving how we might address unanticipated memory problems going forward. So with that, I'll jump into the executive summary for this talk. So the problem that I'm going to be talking about is overcoming DRAM technology scaling challenges. And these challenges are becoming more and more difficult with new problems coming up, and so we need new solutions to address them. So our observation here is that the separation of concerns that exists between DRAM producers and DRAM consumers is actually becoming a barrier to overcoming these scaling challenges. And we make two observations for why. So first, we observe that the separation of concerns is too rigid and actually prevents us from addressing new challenges that come up that we didn't anticipate. And second, the separation of concerns discourages new solutions that depend on cooperation between producers and consumers. So our key idea in this work is to revise this separation to somehow encourage cooperative solutions that are new approaches to addressing DRAM scaling. And so in this work, we performed 4 case studies looking at performance, energy efficiency, reliability, and security problems. And we look at what factors are preventing the industry from adopting cooperative solutions. And based on that, we try and look at how we might revise solutions to overcome those problems. And through these case studies, we identify memory testing as the core culprit for actually preventing us from adopting those solutions. And so I'll talk a lot about memory testing in the latter half of this talk. And so finally, we conclude with a 2-step approach to revise this DRAM separation of concerns. And it's divided, sorry, am I covering up the slides if I'm standing there? Yeah. So it's divided into a sort of near-term and a longer-term approach, where in the near term, we focus on trying to avoid making changes to the DRAM hardware, but rather enabling these cooperative solutions. And in the longer term, we would like to revise standards so that memory chips going forward are inherently encouraging cooperative solutions. So here's a quick outline of the talk. And so I'm going to start off with some background about DRAM scaling challenges. So DRAM is central to all manner of computing systems today, and it has been for a long time. So here I show memory, computing systems back from the 1970s to today, and DRAM has played a major role in all of these systems in different forms. And just to give another example data point, over half of the memory that's produced today it is DRAM memory, right? And so it captures over half of the global memory market, and the remainder of that is actually NAND flash memory. And so these two together form sort of the main memories used today. So across these decades, computing systems have benefited from generational improvements to memory. And so here I'm showing an analysis of the capacity of DRAM systems over time, bucketed into groups of 5 years each. And so what we see here is on the y-axis, the capacity of each DRAM chip, and on the x-axis, the date. And we do this using a best effort survey of memory data sheets. So we go look at data sheets for memory chips throughout these different time periods. And we can't guarantee that's the actual manufacturing date, but it's a proxy for what we're looking for. And what we observed is that capacity has been increasing exponentially over time. And since the inception of DRAM back in the 1970s or so, we've seen over 1 million times improvement in storage capacity. This is a huge number, right? So this, the industry has generally benefited from this improvement being steady over these years. And so the next thing we look at is timings. And so here on the y-axis, I show timings in nanoseconds. And what these are is they're essentially rules for how we can access the DRAM memory. And so these 4 timings that I showed here can essentially be thought of as a proxy for DRAM performance. And so they define how quickly we can access the data that's stored in DRAM. And so what we see is something similar here, where there have been steady improvements to the access latencies over time. And basically, across the span of this plot, we've seen about 8x improvement, right? So even here, similarly with capacity, we see improvements to latency over time. Now, the problem here is that if we look at the last 2 decades or so, these improvements have actually slowed down quite significantly, especially with respect to latency, which really doesn't seem to be improving too much at all. And so this is sort of the core focus of the talk. Why is this happening? Right? So Okay, so this process of improving across different technology generations is what we refer to as DRAM technology scaling. And so this technology scaling has traditionally been driven by DRAM manufacturers because it takes very specialized knowledge and technologies to build highly efficient DRAM. And so this specialized group of manufacturers keep improving across different generations by improving on their own circuit designs, their own manufacturing techniques, and so forth. And so scaling has been traditionally driven by these manufacturers. And so what they've been doing is taking a tightly packed storage array of DRAM cells, where each cell stores a single bit of data, and using different circuit level techniques, materials, fabrication methods, and so forth to improve the storage density of chips over time. So this 2D array here basically gets compressed into a denser and denser form, enabling us to store not just kilobytes or megabytes, but today gigabytes of data. So the problem here that prevents us from indefinitely doing this is that DRAM suffers from a variety of different error mechanisms that cause reliability problems. And so these errors can actually corrupt data that's stored in the memory chip and result in data loss or system failure if we just ignore them altogether. And from looking at the perspective of the storage array, essentially each cell is susceptible to a variety of different internal and external mechanisms that can corrupt the data stored in the cell. And so this essentially means that the technology scaling that manufacturers are trying to do over time becomes more and more difficult because as they make denser and denser storage arrays, more of these reliability problems crop up. And so over time, the chips overall become less reliable, and we need to find solutions to prevent that from happening. So the takeaway there is that continued scaling becomes more and more expensive as we try and go further. And this is primarily because of the overheads of trying to maintain reliable operation. So here I'm showing a couple of different mechanisms that manufacturers have been using to enable reliability while scaling. And so I'm showing the graphic of error rates ranging from low to high. So when error rates are relatively low, no mitigation is necessary. So way back when, during the beginnings of DRAM technology, this is how most DRAMs were produced. There weren't really any significant error mitigation mechanisms. It was just a raw storage array that you can interact with. And you didn't really have too many reliability issues like you see today. As things progressed, stronger and stronger error mitigation mechanisms were necessary. So one of the earlier ones that's used is what's called row column redundancy, where manufacturers provision spare rows and columns within the storage array so that when errors are found, those rows and columns can be replaced with the redundant ones. Right? So this allows us to correct errors at a coarse granularity and deal with some reliability problems. But when errors become even worse, we need finer grained solutions. So the next level of finer grained solution that's been used in today's DRAM chips is error correcting codes. And here, instead of operating on an entire DRAM row, which can be kilobytes in size, we operate at the granularity of an error correction code word, like an ECC word. And what we do is essentially, instead of storing data directly, we store an expanded representation that's more resilient to errors. Now, when errors become even worse, today we're seeing more active solutions which operate only when we observe errors actually happen. So whereas spare rows and ECC are provisioned for all locations of the memory, these active solutions try and focus repair resources only on the locations that fail. But the cost of these mechanisms increases as we go down this hierarchy. And looking forward, when errors become even worse, it's not really clear how we should proceed. Because if we keep using more and more heavyweight mechanisms, eventually the costs of those mechanisms will begin to outweigh the benefits that we actually get from all of this. And so it really comes down to, is it worth it? Like, how far should we really go with this? So more generally speaking, there's usually 4 key challenges that we identify with DRAM technology scaling. And this is when these memory cells have become so small, they're exhibiting lots of different types of errors, and we run into all sorts of challenges that stem from these errors. And so the key ones here are performance, efficiency, reliability, and security, and they relate respectively to memory access latency stagnating, like I showed in the graph earlier, the overheads of performance and energy when we're using DRAM refresh, which I'll talk about later in the talk, reliability, just mitigating these errors to begin with, and security with problems that are coming up, such as row hammer. So here, I'm going to go back to that plot that I showed earlier. And essentially what we're focused on is the fact that for the longest time, these generational improvements were driven exclusively by manufacturers influencing these mechanisms. But today, we're seeing slow progress, and we need to find other ways around this. And so we can't really rely only on manufacturers to continue this process, and we need to have sort of creative thinking going on. Okay. So the next part of my talk, we'll talk about addressing these scaling concerns, and in particular, introducing this separation of concerns. So I'm going to start with talking about the relationship between DRAM producers and consumers. So DRAM producers are the people who actually manufacture the DRAM chips. And today, we essentially talk about the three major DRAM manufacturers, right? Samsung, Hynix, and Micron Technologies. And so these people are essentially responsible for producing highly efficient commodity DRAM that's on the market. The next part is DRAM consumers, who encompass pretty much anyone who consumes DRAM chips in the course of their work. So this could be system designers who design boards or processors or what have you, test engineers who test and validate systems that use DRAM, and even research scientists who study DRAM technology to try and make improvements across generations. And so this divide between producers and consumers allows each party to focus on their respective problems, right, and specialize in their roles. So the thing that makes all of this work is what we're calling the separation of concerns. And so DRAM design is a concern that's left for the producers, and DRAM use is a concern that's left for the consumers. And ideally, there would be no overlap between these, right? So each party can focus on what they're best at. And what this enables in general is that this specialization of roles allows each party to build highly optimized chips that alternatively might be very difficult to do if we're trying to focus on multiple goals at the same time. The second thing here is that this separation of concerns allows interoperability between memory chips that are produced by different manufacturers. And so this means that DRAM can be widely used by all sorts of computing systems because they can basically take whatever's on the market and integrate it into their design according to fixed specifications. And the third part here is that it also preserves trade secrets that both producers and consumers might want to keep because this affects their competitiveness in the market and how they can essentially produce the devices that they produce. Right, so all of these are benefits of the separation of concerns. But the problems that we're seeing today indicate that trying to address all these problems just on the producer side of the problem gives us a very limited solution space for trying to come up with mechanisms to continue scaling, right? And that points to another concern that the separation of concerns itself is becoming a barrier to addressing these scaling challenges because it's not allowing both parties to interact in order to address these problems. So the two major observations that I mentioned in the executive summary are essentially supporting evidence for the separation of concerns being a problem. So the first of these is that the separation of concerns is inflexible when we're faced with new challenges that we didn't anticipate. And so examples of this are Rowhammer, which I'll talk about later, and a lot of people here are quite familiar with, and this general problem of worsening memory errors, which we understand that they're going to become worse over time, but the rate at which they're becoming worse and how to deal with them is something that I would say that we were not fully prepared for, right? And so when we need to deal with these challenges now, the separation of concerns makes it quite difficult because we're isolating the ways we can solve the problem. The second observation here is that the separation of concerns constrains the solution space we're working with. And I mentioned this in the previous slide, basically, right? We're isolating solutions mostly to the producer side and relying on solutions there. But based on what we're seeing today, it doesn't seem like this is sufficient. So I'm going to talk about each of these individually to give some examples and some more detail. But are there any questions about what I've covered so far? Or anything to come up? Yeah, okay, I'll move along then. So first I'll talk about this first problem, the inflexibility to new challenges. So I'm going to introduce DRAM standards, which really are the tool that enforce the separation of concerns. So some of you might have seen, right? So I have some pictures here of JEDEC standards that we use today. There are older DRAM standards, such as the RAM-bus standard, and even standards put out by other consortia beyond JEDEC. For example, the HMC specification. And all of these documents essentially set guidelines to separate the concerns between producers and consumers. And they essentially implement the separation of concerns that I've been talking about. So the standards basically govern every consumer visible property of a DRAM chip. That's its ideal goal, right? And so this includes things like the interface observed by the consumer, the way that the consumer will configure the device to perform a certain function, and the performance characteristics expected from the memory device itself. And so producers can target all of these goals in building their chips, and consumers can simply use it as is and know exactly what they're getting. And so this provides a separation of concerns. And at the higher level, what it does is it abstracts all of the design, the DRAM design concerns away from the consumer, so they don't have to worry about it. They can simply have access to highly optimized DRAM. So here's an interesting piece of data that we collected as part of the datasheet analysis. So here I'm showing the length in page numbers, in page count of the different DRAM standards that we've seen and the release date for them. And we kind of observed that these are becoming much, much longer, right? And actually fits an exponential trajectory quite well. So it's not clear what we can conclude from this, right? Because there's elements of complexity, right? The standard is simply more complex. There's more features that need to be encompassed in this document there's new issues that are covered by the document. But it is interesting to see that, these standards are becoming more and more difficult to deal with. As a consumer, you now have to, instead of a much simpler standard, you have a much more complicated one, and there's just a lot more going into this problem. Okay, so this brings me to the point of the problem that I'm trying to observe, the problem that we've observed here, which is the inflexibility of the standard, right? So what we really see is that the standards appear to be slow to change, right? And so when a new problem comes up that we haven't been thinking about, it actually requires industry-wide consensus to change the standard to address that issue. And this process takes a really long time because we have all the producers and all the consumers who need to agree on how to best solve this problem. And if the problem is not well understood to begin with, there's no clear path to the solution. And all of this just takes a really long time to adapt when new issues come up. So I'm going to give two examples of what this slow adaptation is. So here there's a timeline, ranging back from about 2014 to today. The first example is Rowhammer, right? So Rowhammer security vulnerability. So it was first sort of publicly disclosed in 2014. And since then, it took a really long time to actually see signs of Rowhammer being addressed in the field. Right? So around 2017, I think there's some data sheets that start mentioning Rowhammer-free chips, which in theory are immune to the issue, based just on producer solutions, right? So producer-only solutions. But even after that, it took a long time for more interest to develop in this space. And only recently, in the past few years, have we seen action in terms of modifying the standards to address the Rowhammer problem. And so we've seen that there's a task group within JDEC. There's new mechanisms provided by the standard to help us address the Rowhammer issue. But this is quite a long time span we're talking about, right? 8 years overall. And things have moved quite slowly for an issue that academia has been studying quite rigorously across these years. The second example I have here is on-die error correcting codes, which around a similar time frame, 2014, we started seeing manufacturers write papers. And for example, ISSCC here, the DRAM producers themselves described potential designs to address scaling concerns in the future by implementing error correcting codes within the memory itself. Right, so we didn't actually see them used in chips until about 2017 with LPDDR4. And at that point in time, it seemed like a great solution. It addresses errors at a scale that we previously couldn't address, and we'll just move forward with this. But starting around 2019, 2020, we started seeing the downsides of having this black box ECC within the memory chip. And it actually made the overall reliability characteristics of the memory chip less predictable. And so there have been some papers that talk about this across the years, but we didn't really see the standards start moving in this direction until 2021 and thereafter, with the HBM3 standard and DDR5 beginning to talk about the fact that it's important to disclose this information so that the consumers know what's going on and can design their own solutions around it. So in both of these examples, there was a really long time between when the issues were sort of considered and first discussed to when the standards actually changed to implement them. And so this is the problem that we're observing. And even today, I would say for both of these, we don't really have a complete solution that everybody's happy with, right? There are measures to address this and more interest, but we're still working on these problems. So the second problem here is this problem of limiting the solution space available to us. So I'm going to introduce the general concept of system memory cooperation as we're talking about it here. Right, so the goal here is to use information from both the producer and consumer side to address these scaling issues. Right? And so by pooling these two together, the hope is that we can come up with highly efficient solutions to address these scaling challenges that are based on a wider understanding of the problem and how it actually impacts the system, as opposed to each party trying to come up with solutions on their own. Right? So the literature has many proposals for system memory cooperative solutions to address scaling challenges across the past decade even. And so we're going to talk about that a lot here. So some examples of what this might look like is, for example, to improve performance and energy and power, we might exploit slack in operating conditions for the DRAM chip. So the recommended operating conditions might say, operate your DRAM chip in this way, but it's a very conservative approach. Right? You don't actually need to be that conservative in all cases. And so by knowing how the system is going to make use of the chip, we can take advantage of this slack and improve one of these system level metrics. And so examples in the literature where this has happened is with access and refresh timings, with operating voltage and temperature. And these are all areas that we can potentially operate the chip differently if we know our use case, which is different from what the standard was necessarily designed for. Another example is with reliability. So if we're not happy with the reliability that the DRAM chip produced by the producer provides, we can build additional mechanisms to improve reliability beyond that. Doing so is sort of a very open-ended problem because we can implement mechanisms that live right next to the DRAM chip to address issues. We can implement higher level solutions like all the way to the software. And all of this relies on a combination of knowing how the errors are occurring and then how we can efficiently address them. And the third example I have here is security, which, for example, implementing Rowhammer defense mechanisms is again a cooperative problem because we have to understand how the errors occur so that we can successfully address them. Yes.
I have a question. I guess it's going to come up later. Yes. In this slide here, it's clear like the parts that like the system can improve some particular metric, but it's not so clear like what the manufacturer should provide so that the metrics can be improved. So I guess we're going to talk about testing. So.
Yes, absolutely. I think this is one of the key things with this work that, so this work in general is a work in progress where we see the problem, we kind of understand what the issue is here. But as far as like how to resolve it, that part's very open-ended right now. So I think later in the talk, I will very much talk about, potential ways we could help communicate information such that these particular use cases become more easy, right? So we can implement mechanisms like this. But if we start talking about mechanisms that aren't on this list and ones that haven't been discussed in the past, that's the very open-ended problem because now we're trying to anticipate issues that we don't know about yet. And so how can we prepare these standards or the separation of concerns in a way that when we do encounter an unforeseen issue in the future, we will already have the tools to address it, as opposed to just the tools that we've been looking at for the past 10 years. Yeah, does that make sense? Yeah. Okay. All right. Yeah, so I'll move on. So the problem with system memory cooperation here is that the separation of concerns actively discourages taking this sort of approach. So here I have this diagram that I showed earlier with the separation between producers and consumers. And in order to use these kind of solutions in practice, we need some sort of communication between these two parties. Like, for example, with the Rowhammer case, we need some sort of way to figure out how the errors look so that we can address them. And so the consumer can try and do that by themselves by reverse engineering characteristics of the device and running extensive studies. But all of this discourages the consumer from trying to pursue a solution because there's so much undefined work that needs to be done, right? It's hard to say that, okay, we have complete knowledge and now we can pursue a solution based on that knowledge. Whereas through communication, we could potentially achieve this. But the separation of concerns actively prevents this from happening, right? Because each party is only concerned about their side of the problem. And so what ends up happening is that each of these parties doesn't really have insight into what the other party is doing. The DRAM consumers have no or minimal insight into the DRAM design, and the DRAM producers have very little insight into how DRAM can be used in different ways. And ultimately, this is, okay, yeah, sorry, I have to move on. So this is another way to visualize the same problem. So imagine this gray space is the space of possible ways we can operate DRAM in a system, right? So I call them DRAM operating points. So the standardized operating points shown in blue are what the separation of concerns gives us today. So operating within this space is very good because we understand exactly what needs to happen. The specification tells us what the DRAM device will look like, how it will behave. So the cooperative solutions we're interested in currently live outside of this space because we don't have all the information we need to actually pursue these sorts of solutions, though it is theoretically possible, right? So I'm trying to look at this in terms of the total cost of ownership or TCO. So in the standardized operating points, we're essentially encouraged to pursue these designs because they have a low TCO, right? And so from the perspective of the producer, the DRAM design that they provide is fully contained within essentially the manufacturing location, right? So the people making the DRAM chip, it's all trade secret. They know exactly what's happening. And whenever an issue happens, they can go debug it because it's their design. They have full control over it. And from the consumer's perspective, the DRAM chip that they're using that's compliant with these standards is fully supported by the manufacturer. So if there's ever an issue, they can just turn to the producer they got this from and say, hey, there's a problem. Can you replace the part for us or warranty? Whatever the mechanism is for this, it's essentially a way of doing business between both these parties that works very well, right? And that's what the system is set up for. Whereas the cooperative solutions here, and generally this whole operating space outside of the standardized regime is discouraged because we'll say it has relatively high TCO. And for the producer, this means that the consumer could be using their device in any way that's outside of specifications. And so it's difficult for them to give a guarantee that if you run into a problem, we can figure out what it is or replace the part for you or something like this. And for the consumer, this is simply outside of the knowledge that they have about how the DRAM device will respond to these operating points. Right? So neither party has a clear idea of what's going on. And unfortunately, because these cooperative solutions live within this unstandardized space, they are also somewhat discouraged. So our key idea here is to try and encourage these cooperative solutions. And how exactly to do that is the focus of the rest of this talk, right? It's sort of still an open-ended problem that we're trying to flesh out. Some ideas that we have right now is that in the near term, we can potentially do this not by touching standards, but rather by touching the cooperative solutions themselves. And so we can try and expand the space of cooperative solutions so they overlap with standards. And in this way, the intersection of these two now becomes a point that's no longer discouraged, not necessarily encouraged, but perhaps something in between. So it's something that's much more feasible. And in the longer term, we're thinking that we can actually request changes to these standards so that they encompass the cooperative solution space. And this is a longer term solution because again, it requires this consensus between all the stakeholders in the industry. But if we can design this in a way that cooperative solutions themselves are encouraged, we believe that this cycle will sort of reinforce itself, that once we start having cooperative solutions, we know better how to build them, we can incorporate them into standards, and it's sort of a virtuous loop. And so essentially this overlap space is what I'm highlighting here. So ideally we would like these spaces to be encouraged, right? So that's our goal. Yes.
Sorry, this is naive, but since the two are together, if the incorporating solutions are the standard, isn't that also going to make the standard such for complex 1,000-page standard?
Yeah, potentially. Yes, that's definitely a problem. So I think when I showed that figure earlier, right, about the standard length as potentially a proxy for complexity, it's not. I wasn't trying to say that this is necessarily a problem, right? It's simply an observation as it stands. And there's so much going into this that when we look at cooperative solutions, it's no longer just the interface and the performance characteristics. Now it's potentially the intersection of every DRAM that's built and then how all the different ways it might be used, where previously it was only used in sort of one fixed manner, right? So yeah, potentially you could be looking at sort of a combinatorial space that the standard needs to handle. And so that's sort of infeasible, let's say, maybe, right? So those are the kind of things we're trying to think about. And I'll touch on that a little bit later in the talk, but I think there's no clear answer to that question. Yeah.
So this is another question really, but like we think about this sort of picture you have. So when you think about Rowhammer, the standardized operating points, I think maybe you add another layer there and say advertise standardized operating points, and the actual standard, actual operating points were kind of
I see.
those smaller scope than the advertised, and then cooperative solutions could help you actually get to that advertised point maybe more easily in that case. Because what I'm thinking right now is, you said that DRAM wouldn't have any errors, right? As a manufacturer, if you obeyed all the timing parameters and kept the DRAM temperature under this and that, but there happen to be errors. So your actual operating points were much less open your standardized operating point.
Yeah.
I don't know where to go with this, but this is what I was.
No, I think it's good. Yeah. So this is something that, yeah, as I said, still in flux. But yeah, so if I understood correctly, you're saying that the standardized operating point doesn't actually reflect what we see in the field.
Yeah.
And so it should somehow be broken apart into a third category.
But we don't know why it doesn't also at
Yes.
the same time. So it's
Yes.
another thing you mentioned. So we want to predict. Well, we cannot predict, but how do we foresee the next reliability problems we will have? We need some sort of a leeway, I guess.
Yeah, something between these two extremes. Yeah, I think that's a good point. Yes. Yeah, so I was reminded that I should repeat the questions every
This is
time.
another question.
Yeah, this was a comment. So I think just to summarize the discussion here, essentially what we see in the slide here is we have a standardized operating point that standards call for, and then cooperative solutions, which is something we'd like to have. But there's actually a space that's in between, right? Which is that we have the standardized operating point that says things should be like this, but in reality, we observe that there are actually some errors that make it to the field, which are sort of outside the standard, right? Because the standard doesn't provision for these. It says essentially these shouldn't really be happening. So in reality, we, I guess, have a third point somewhere in between, which I guess is part of the interplay between all these factors. So I think that's a very good point. Okay. Are there any other sort of comments on this?
So,
Yes.
maybe we'll come to that, but,
Right.
do you have any examples of like, for the recent, among the recent developments, do you have any examples of these cooperative solutions? So for example, in the domain of programmer, there was this, the refresh management thing, introduced it with DDR5, right?
Right.
Can we identify, classify it as a cooperative solution, or, is it not what you mean?
Yeah. So the question is, some recent solutions that we've seen, like the refresh management in DDR5, do these classify as the sorts of cooperative solutions I've been talking about, or is that actually sort of different than what I've been referring to? I think so. I don't have an example for that in the slide, right? I kept the slides relatively high level, and there's an example later on DRAM refresh, but again, it's not like current solutions that are being pushed out. I think it does fall in the category of cooperative solutions. It's a very limited form of a cooperative solution, I think, because usually these cooperative solutions are more focused on, let's say, complete solutions, right? It's that a consumer has some use case in mind that can take advantage of certain ways that they're going to use the DRAM, right? And that enables them to optimize upon the commodity DRAM that's provided by producers. Given that RFM is sort of just for all devices at all times, it's not really the level of optimization that I think I was referring to, but I think it does fall into this category of pushing the standards out to start encompassing cooperative solutions. Like, I think it goes very much in the right direction.
Thanks.
Yeah. Okay. Yeah. Sorry, was there a hand back there? Oh, okay. Okay, I'll move on then. So the next part of my talk is about enabling system memory cooperation. So in our paper that we're working on, we have we sort of look at this goal where we're trying to look at how people are approaching system memory cooperation and how they have been sort of, both in the literature and in practice throughout, say, the past decade, and look at why, or like what's holding these solutions back from adoption, right? What are the actual constraints that stops us from just, taking a solution, popping it into a system today? And so in order to try and achieve that, we conduct 4 different case studies in our paper of these 4 different areas that I mentioned as key areas for DRAM scaling, right? And so for each of these, we review prior proposals for, improving that dimension of DRAM scaling, and we look at what's holding it back from adoption, right? So in this talk, I'm going to focus mostly on this efficiency one, which specifically is going to deal with DRAM refresh. And I'm just going to give a quick overview of the kinds of things we're looking at in that space. But yeah, I'm happy to talk about the others or discuss it further afterwards if you're interested. So to focus on this case study on mitigating DRAM refresh overheads, I'm going to give a bit of quick background on DRAM refresh itself. So here's a picture of a DRAM cell. Internally, it uses an access transistor and a storage capacitor, and it uses this combination to store 1 bit of data. And the way it does this is that using the capacitor, it encodes that piece of data either as charge or discharge, a 1 or a 0. And this depends on the particular circuit implementation. But essentially, we encode the data using the charge of the capacitor. Now, the problem is that every capacitor is intrinsically leaky, and so it leaks charge over time. And so what we start out with as, let's say, a fully charged cell eventually degrades, and then we can no longer tell what was originally stored in this cell, and we call that a data retention error. Now, to prevent this from happening in practice, the memory controller usually issues a process called DRAM refresh, which periodically restores all the capacitors to their initial state, whether that is charge or discharge, depending on what was stored there. And so this process is rather expensive, and it happens quite frequently. So for every cell in the memory, right, this could be billions of cells. This happens, on the scale of like tens of milliseconds. And so as you can imagine, this results in a lot of performance and energy overhead. And so to provide a little perspective for those numbers, here's some data that's taken from one of our papers a while back. Here we're looking at the average system performance overhead of the system relative to a baseline that doesn't use refresh at all. And for different DRAM chip sizes on the x-axis, we see that this overhead becomes rather significant, growing into the tens of percentage points. And this increases with chip capacity because there's simply more cells to refresh. Right? So as we move to denser and denser chips, this overhead becomes worse and worse. And so we really want to look at ways to avoid this overhead wherever possible. So one of the main observations that a lot of works use to build better refresh mechanisms is that most DRAM cells actually don't need to be refreshed that frequently. So here's some data from the same work where this is an experiment that we ran on a real chip. And we observed that as we increase the refresh period from the default, which here was 64 milliseconds, to a factor of 8 longer, 16 longer, and so forth, when we increase it by a modest amount, we see very few actual failing cells, right? So this is 100 cells out of the entire memory, right? Where in this case, the memory, I believe, was 8 gigabytes. I think I'd have to check the work, but it's out of a very small fraction of cells are actually failing, right? And so we can use this observation to identify those cells and just essentially increase the refresh period and deal with the few failures that occur. And so what that kind of looks like is that we have an array of cells within the memory device, and each of these cells has a different leakage rate, different leakage properties, different size to begin with. And what we want to do is we want to identify the fast leaking cells, say, which here I show in red, and there's a few of these throughout the memory array. And so this is where the problem comes with the separation of concerns, because identifying these particular cells is actually a very difficult problem that essentially relies on memory testing. And the problem here is that in order to conduct memory testing in a way that you can depend on the results, you have to know more information about the internals of the DRAM chip. And so this could be as simple as the internal layout of where cells are in the memory, because this is different from what you see from the software, right? It could be something as detailed as circuit level characteristics of the cell, right? So certain properties that cause a cell to leak more often, or perhaps its physical position in the array, which affects its leakage rates. All of this kind of factors together to make this a problem that for a consumer is very difficult to do without insight from the producer, because the separation of concerns doesn't communicate any of this information to the consumer. And so we can essentially say that this whole process of identifying cells and trying to mitigate them is unsupported by the separation of concerns. And if a consumer wants to implement this sort of mechanism, they have to do so outside of the standardized operating point, okay? So to give this a little more formally, the problem that we face here is that when we start with a DRAM chip, right, that's used in a particular system, we want to identify the weak cell locations. And there's two major ways we can do this. And both of them start with looking at the structural properties of the DRAM chip itself, right? These kind of characteristics I talked about, the physical locations of cells and things like this that we don't necessarily have direct access to. The first approach is through testing, where it's kind of like I described in the previous slide. We need to come up with some kind of test methodology that we trust, and then run that test in order to identify the locations of weak cells. And so this is an approach that's taken by a lot of research scientists because they can test the memory chip in the field and look at its properties and come up with mechanisms based on what they learn. The other approach is based on modeling, right? And so the problem here is that even taking this approach, developing the models themselves, or parameterizing them with the parameters that we need based on a given DRAM chip, they require access to the same sort of information. It's this information that we essentially don't have access to. And using that information, we can develop all sorts of models for how these errors might occur. And again, based on those, we can then predict weak cell locations. But either of these approaches is sort of inaccessible to us because it violates the separation of concerns. Right? So going back to this, I guess these examples I gave earlier, the same story is true for pretty much all of these cases. At some level, they rely on knowing information that the separation of concerns doesn't provide. And so it's very difficult to adopt these systems in practice outside of a prototype or some demonstrative exercise. I think going back one step higher, like the DRAM scaling challenges that we mentioned earlier, what we essentially figure out is that these are all discouraged, right, by the fact that the standards remove this information from what's accessible to consumers. And so yeah, so this is sort of going full circle with what I said at the beginning, right? With the standards, the separation of concerns, not being transparent about what's going on to either party.
I have
Yes.
a comment to make.
Yes.
Answer your question. But I think to add on top of this, there is also the problem that you can do testing or you can do modeling. But in the end, as a consumer, you actually don't know if you are testing or what modeling exactly is what you're aiming for, because the device is a black box. Right? You can have a model or testing strategy to some significance on your results or how much you can trust the result that you actually did what you're expecting. But the truth is that you don't have a ground truth to compare against, right? So like validation of that model, validation of the test structure is just our best effort that the consumer can do, right? You comment a little bit on?
Yeah, I think so. There's a slide I'd like to pull out actually. So the question here was that regardless of how much modeling and testing a consumer might do, ultimately the DRAM chip is a black box. And we can't ever really say whether those models or those test results are truly accurate in the way that we want them to be. So the slide I wanted to pull out is here. So this is a figure that we have in our paper, actually. And we try and sort of say this in the sense that, okay, so all the different pieces of information we have here, right? So for example, the chip design properties, we have some examples. And we also have some tables of this data based on what we've seen in, I guess, in prior research studies. The same for all of these, right? Error models and parameters, test methodologies, so forth. But yes, ultimately, this is the core challenge, because no matter how much of this you do, it ends up being speculative in the sense that you don't actually know whether you can trust this information, right? So what we explain sort of in the paper is that there's a dependency relation between these pieces of information, where if you manage to figure out any piece of information in this data flow in sort of a reliable way, then you can build on top of that information to get to the end result that you want, right? So maybe you don't know these basic chip design properties, but you do know that a particular analytical error model is correct, right? So then you can skip the need to even have that information, and you can work with the model that you have and the parameters for the models that you're given. But the problem is getting this point of trust where it's like, okay, I know that I can rely on this piece of information, so I'm going to build on it. That doesn't exist because everything is hidden by the separation of concerns. And so I think this goes back to one of the questions that was asked earlier. Like, if we don't know what information we need to communicate, then what should we do, right? So I think what we're saying here is that right now, everything is sort of hidden. And if any of it is sort of released, it's already a big step forward, right? So if we know any piece of information, we can build on top of it. And I think that's where I'm going to go in the later part of my slides. So I absolutely agree that, you know, if you're doing your own study without having any of this information, you're either making assumptions or you're sort of not super confident in what you're observing. And at that point, it's just a judgment call. But with access to the actual information, you can be at least as confident as the manufacturers are when they sell you memory. Yeah, so let me go back to where I was with this. Okay, so yeah, we talked about that. Okay, are there any further questions? Okay, so I'll move on. So the last part of my talk is about revising the separation of concern. So I think, you know, through the questions, we've already looked at a bit of this. But I'll just go through what I have here. So the main question is, you know, okay, we know that we want to revise it somehow to provide some sort of insight between the separation of concerns, but how should we do this? We have some sort of general principles that we're trying to adhere to. So in the near term, we want to make sure that what we propose is practical, right? So we have these three properties here. So the fact that it's achievable means that it doesn't rely on changes to DRAM hardware, because that actually requires a long design cycle from manufacturers, adjusting potentially the separation of concerns already. And so that's not a short-term solution anymore. It needs to be practical in the sense that it doesn't go exactly opposite to how the industry is set up today. So for example, with trade secrets, this is a big deal for the memory manufacturers because they rely on these trade secrets to remain competitive in the market. And if we say that, oh, you should suddenly reveal information that you consider a trade secret, it's really not a practical thing to ask for because there'll be lots and lots of pushback, and it's not something that we can hope to do very quickly in the near term. And backwards compatibility is also another characteristic that we believe is pretty important, because we shouldn't force all consumers to have to think about how do I want to work around these cooperative mechanisms. For the majority of them, potentially, they still want to continue using memory as is. So we want to make sure that, you know, we don't violate any of these properties. For the long term, we believe that recommendations can be more encompassing. So it can violate some of these properties from earlier. You know, we can request changes to hardware, we can request changes to standard. But the question is, what should we request to move through this problem? And so what we talk about in our work right now and what our thoughts are is that for the near term, we want to focus purely on information transparency. So don't try and modify standards, don't try and modify hardware. Just focus on some limited information transparency between producers and consumers. And for the longer term, we try to focus on changes to the memory standard, as opposed to saying specifically what changes should happen to the hardware. And I'll talk about both of these. The general thought process between the short-term and long-term approach is that based on the solutions that sort of the research community, industry, everybody comes to based on the information transparency, those can all be used to inform how we should move forward with DRAM standards. It sort of paves the way bit by bit, right? So we're hoping for this sort of connection between the two. So to talk a little more about our near-term revisions, to look at what sort of information we would try to communicate, we try and study the practicality of information transparency itself, right? So we can have different levels of information transparency from the producer to the consumer. And this can range from today's black box sort of setup all the way to a completely white box mechanism where DRAM is effectively open source and you know everything about the circuit design and whatnot, and then something in the middle. So a couple of categories that we think about are, for example, the burden that this produces on the producers and consumers, and third, how it affects the encouragement or discouragement of system memory cooperation. And we see that there's, both extremes are sort of not the best in certain dimensions. So what we have today, clearly discourages system memory cooperative solutions. What we would have with a sort of white box solution is a big problem with the practicality of doing this, because a lot of the DRAM optimizations and everything come from manufacturers optimizing things internally and having control of the product. And so we're looking at something kind of in the middle, where there is additional burden on the producers to communicate some information, but not so much that it becomes prohibitive to adopting this sort of approach. The consumer burden is, again, sort of variable depending on what the consumer decides to do. So if they want to just continue using memory chip as is, or if they want to implement cooperative solutions, presumably it'll be more work, but again, not discouraged in any way, and potentially encouraged. So these are our thoughts about what sort of information to release. And we're focusing on this middle ground here. And so to identify the actual information that we'd like to communicate, we're focusing on design and test, right? So this is going back to what I mentioned with our case studies, where we're looking at what information is holding back progress in adopting these cooperative solutions. And so here, we try to focus on specific pieces of information that are already available, right? So properties that can already be reverse engineered and are done so by sort of, these prototype research studies that are done in the field. Because this information is no longer secret, right? It can already be reverse engineered. We know how to do it. And so even though it might have been considered a trade secret at some point in time, we have reasonably reliable methods for accessing it. And so the theory is that, okay, this probably won't put too much of a burden on manufacturers because they have this information available even for past designs, and they can provide it because we can figure it out if we really need to. So it shouldn't encroach on the sort of trade secrets that the industry is relying on at this point in time. And so in the paper, we talk about, what these characteristics might actually be. And, it's a lot of the stuff I talked about with the modeling and testing from earlier, the details of how exactly things are laid out inside the chip, certain properties of how data is encoded amongst cells and so forth. And so we talk about what those characteristics are, studies that reverse engineer this information. And then we go over different proposals that rely on knowing this information to demonstrate why this information might be useful, right? So these are our thoughts on the information that needs to be released. And I just want to quickly refer back to the question that was asked earlier. So this is all information that is known based on the last decade or so of studies, right? So we know that these use cases exist, and we sort of have a good idea of what it would take to adopt them. But for future problems that might come up, we don't have solutions yet. We don't know what it would take. So that, I think, is an additional part of the challenge. Like, is this list sufficient for, sort of future proofing, or are there additional things we should opt for? These are thoughts that we're still considering, and be happy to have input, really, if anybody has any thoughts on it. Okay, so now I'll go back to this two-step plan that I presented earlier. So the near-term plan was to sort of, make more cooperative solutions possible, and the longer-term plan is to encompass those solutions within standards themselves. So the near-term plan focuses on this information transparency that I just talked about. And so we propose communicating information in two ways. And the goal of these two different ways are to sort of avoid the need to change standards, right? We're trying not to change hardware or standards here. So the first is to directly ask for this information from manufacturers who could communicate it through white papers and data sheets and things like that. And the second is a sort of crowdsourced database that can be put together by consumers. Because we've seen, even in our lab, we have access to a lot of this information, and we spent many years studying it. There are other labs that have been doing the same thing. Industry has been doing the same thing, like large-scale consumers of memory chips. They do their own testing of memory chips. So potentially pooling this information together could be a strong step towards encouraging manufacturers to release this information at all. Or at the very least, make it easier, because then they can simply verify the information as opposed to having to, come up with some way to release it themselves. So this is our thoughts for the short-term solution. And for the longer-term plan, we hope to modify the DRAM standards in a way that they grow to be more encompassing. And we would like this to incorporate all of the testing and modeling and reliability information that I talked about earlier. So how exactly to do this? This is very open-ended. We believe to some extent it will organically grow out of cooperative solutions. So the short-term solution that we present, mechanisms that are built using the information that we now have available can then inform what we want for changes to standards, right? So the ones that end up being more promising, perhaps are the ones that will influence the standard the most. That would be a very empirical way to go about this. More sort of a more principled way to go about it might be to try and anticipate what problems might occur and then what information we might need for that and make sure that's part of the standard. But again, it's very difficult to do because it relies on sort of predicting the future, right? Which is always kind of a gamble. So those are our thoughts for this two-step plan. And so, yeah, go for it.
Don't you think the warranties also need to be extended a bit, like the coverage, to motivate, the consumer that wants to employ cooperative solutions that will be on the boundaries of standardized operating points? Because if by doing that for even like 1 millisecond, like doing that, I mean, operating the chip beyond the standard operating points, they lose warranty. Like, would anyone be motivated to do that?
Yeah, so to repeat the question, so today the manufacturer provides some warranty on their memory chips, and a consumer who's exploring a cooperative solution, potentially even with support of the standards or released information, how would that interact with the warranty? Because the manufacturer probably wouldn't provide the same warranty over the new operating point that's outside of standards, at least for the time being. I think so. I agree. And when I had that slide, let me just go back. I had that slide with the table earlier, right? And so it was sort of acknowledging the point that there is some additional burden for the producer, right? And I think this is part of that, because let's say the existing warranty focuses on, we guarantee that the device that you are purchasing will not experience errors, right? And if it does, we'll use the warranty. I think when we're looking at these more cooperative solutions, perhaps a different type of warranty might be more appropriate, where in certain cases, we will apply the warranty. In certain cases, we will apply not the warranty necessarily, but perhaps some expertise to fix whatever problem is happening. So for example, if, say the example I gave here with the data retention errors, if the customer is sort of reducing the refresh rate in a way that most errors are handled, but sometimes they're not, perhaps the manufacturer can provide additional insight into how those corner cases can be cut, as opposed to saying, oh yeah, we recognize that our product didn't operate how we expected it to, and so we will issue like a refund or replacement or something. So I think the nature of the warranty itself would be a little different. It's almost like a support type thing, which very much is additional burden, but I think it's difficult to say exactly what would be the best way to do that without input from the producer themselves, right? I think it's, I'm no expert in saying what their business challenges are and what they can and cannot support. So I would hope for a sort of open discussion with this. Perhaps this is something for those JDEC committee meetings or something like this, but yeah, I don't have a better answer than that. Yeah, makes sense?
Yeah.
Okay. Yeah, any other questions here? I think we're at the end of the talk then. So the last slide was just a reference to the paper. So we had an earlier version of this work on archive as of about a year ago. We're currently working on revising this and improving it and making changes and things like that. So I'd be really happy to hear from anyone who has feedback or wants to participate or anything like this. Because the idea here is not to propose a brand new way of doing things. It's more reflect on the problem and see how we could do better going forward, right? That's sort of the insight that we're going for. And yeah, with that, I think that concludes my talk. So yeah, thanks everyone for attending. I appreciate it. Were there any YouTube questions? I guess we're on one of them.
Last time I should ever. Okay.
Okay.
So I have one actually, but
Okay.
it's outside of the scope of your talk, I think.
Sure.
So I think your standpoint is really clear, and I am like personally sold the with the idea that this cooperation should exist.
Yeah.
But we're talking about huge companies and a lot of decisions made by just like business mindset. I guess this is similar to the warranties and things like that.
Right.
So at some point, let's say DRAM manufacturers just like agree with each other, saying that we are completely against this kind of cooperation. And whatever problems we have, like reliability problems, we will solve inside the DRAM chip. So in such case, do you see a practical way of extending these interfaces or making, I don't know, JEDEC standards a bit more flexible to allow them with all the flexibility that they need to solve all those problems? And do you think practically they're capable of, I'm not pointing at any company, but
Right.
Is it practical to solve this, all these issues and enable better computation within the DRAM chip without doing this cooperation?
Yeah, that's a very open-ended question. Yeah, I think I understand what you're getting at. So I'm not going to repeat the question, right? It's quite long. But in general, I think the question was that suppose that DRAM manufacturers themselves are not interested in sort of any collaborative solution. They want to handle everything by themselves. So is there any way that then in that world, the consumer can proceed? Is that sort of like the question?
Is it even realistic to achieve the goals that you're putting there, basically?
Yes.
To realize all those, so you had a huge table of of academic works, right?
Right.
So to make them applicable in real life,
Yes.
is it even possible with that kind of?
Yeah. So I think my highest level thought is that ultimately the consumers are buying a product, right? And so they buy that product because it satisfies their needs, right? It provides the level of performance, energy, what have you, that satisfies their design goals. And so we see that. So these proposals that I've listed, right? We don't have really any evidence that many of them have been implemented in products. And so I think that really shows that, okay, so there's a big barrier to adopting these, and the need for these proposals today is not yet high enough to overcome that barrier, right? So adopting this custom refresh mechanism has a lot of risk if you don't have the support of the standards or the producer in general. But you could still go and do it yourself, right? You could, but you'd be adopting a lot of risk for it. And so that trade-off is just not at the point we need it to be yet. But we do have very strong evidence that these errors are becoming worse and worse, right? Like not just the memory errors, right? But other reliability issues within the processor, alternative memory technologies, like these magnetic RAM, all these other alternatives, they also have reliability challenges which are solved in their own ways. But ultimately, if we want to keep pushing the envelope on capacity or performance or whatever for a design, then at some point there's going to be a change in that trade-off, right? It's going to be that, okay, we have to pay more to achieve this level that we want to get at. And whether that payment is in, changes to standards, it's just, stacking additional mechanisms on top, like more error correcting code, something like this. That's really a decision for the designers themselves. So it's really hard for me to answer that part of things. But I do think that the sense that these problems are becoming worse and worse is the key to this. Because at some point they will become more and more, like this discussion will become more and more important essentially, right? So even if manufacturers agree that, okay, today, we can get away with this. We can just say, no, just keep buying our products, don't worry about it. Fine, consumers will probably continue to do that for a while until the discussion needs to be revisited again, where it's like, okay, so your product is no longer satisfying our needs. We have alternative products that we'd rather not move to because we've already put so much work into making this work. There's lots of reasons here for how things could move economically, let's say.
Yeah.
I don't have insight into how that might happen, so I can't really answer that. But I do think it's worth pushing down this avenue, regardless of the attitude of any of these producers or consumers today. Because as it becomes more relevant, this discussion will come back again and again and again. And we are seeing some of this, right? So you pointed out the RFM mechanisms, which are already sort of cooperative solutions. And those are cooperative solutions that are in the standard now. And I think at that time, people were talking a lot about, oh, there's problems with the solutions you're implementing, guys. We need to think about it some more. And then they did, right? They revised the standards. They thought about an interface that was more clean. So it's moving in that direction anyway. I think that's strong evidence that the same thing will continue to happen, where we'll push boundaries on what needs to happen, and eventually we'll need to come to solutions that are more efficient than just either party alone. Does that sort of satisfy the question? Those are my thoughts.
Yes, definitely. It's understandable anyways.
We have a comment or on YouTube that I guess in the same lines of what I just asked. George said, I feel like this is a really hard thing to open up because there is no financial benefit to the manufacturers. DRAM IP is very closed and much different from the post-CMOS process. There is not going to be much movement when the product is so niche.
Yes.
Further public research is required to drive open standards. I guess this is what we're trying to do.
Yeah. So I guess the latter part of that question, we are absolutely trying to do public research to think of better ways to do things. But in response to the comment about the benefits for the manufacturers themselves, I guess so I didn't cover that here. We do address that a little bit in our write-up. I think the core of it is that oftentimes these solutions are driven by research on the topics, right? So the manufacturers basically get a lot of people working on the problems that they need to tackle without them having to invest the resources to do so. Right? So let's say the manufacturers provide this information that I was requesting here, right? This information that can already be reverse engineered in theory. Then we have an army of potential consumers coming up with different ways to leverage this information in the best way. And then whichever ones work out the best, the manufacturers can then build on top of those to provide a better product. So I think it's not entirely to say that, there's no benefit to the manufacturers for enabling others to also work on this problem. I think it's quite the opposite, that researchers are already trying, even though they don't have access, right? I'm one of them, for example. Now with this information, we might have a broader base of consumers also trying to address these problems. And ultimately, I think it serves to strengthen the future of DRAM technology, which presumably is in the interest of the manufacturers. But yeah, I agree that it's without insight from them, it's very difficult to say, and that's, I guess, part of the challenge with this sort of work.
Other more questions?
Anything to add to the existing questions, perhaps? Yeah.
My question is the same, but this is just I mean, coming from a flash memory background, we see that flash memory has more, I mean, especially in reliability with the ECC modules. You see the same happening with DRAM in the long term. And the other question is the second question is we also need to look at ECC and see how we can make it more low latency for the stronger ECC modules and make it low latency for DRAM and
Yeah, so the question is about sort of a comparison with NAND flash memory, right? So in flash memory, we use generally stronger error correcting mechanisms that have been around for a longer period of time. Do we expect that DRAM will kind of go in a similar direction? And is it worth investing in those kinds of resources? So developing error correcting codes that provide lower latency, perhaps more powerful, but suitable for DRAM. I think the high level answer is yes, to both parts of the question, right? So a lot of the research that's happening in DRAM ECC these days is really pushing the boundary of like what has been done in the past. So the traditional system is a DRAM which contains really nothing as far as like ECC goes, but then the memory controller provides some level of ECC, right? So all these terms like chip kill and like, double chip correct, these sorts of things. They're ECC codes within the memory controller to try and handle when DRAM chips fail. Today we see that there's ECC codes on both sides, right? The memory chip contains some ECC, the memory controller also contains some ECC, and the interactions between these become very, very sort of nuanced, right? Potentially interacting badly with each other. So there's work on figuring out how to make those interactions better, but there's also work on figuring out how each side could become stronger more efficiently, right? So whatever is used in the memory today is kind of a black box because it's done by the producers under the current separation of concerns. But there's proposals for, if we did that correction at a larger granularity, we could potentially move the trade-off of performance cost the performance overheads for a certain amount of reliability we gain. In the memory controller side of things, we see work that's trying to go correct even beyond the capability of the ECC code, right? So decoding even when you're beyond the theoretical bound of the code. And all these are ways to address errors that are even worse than what we see today. So I think there absolutely will be a push to look at solutions, not just ECC, but generally all sorts of mechanisms to, I guess, correct errors, right? So there's all these mechanisms that work not through error correcting codes, but more through actively tracking, like predicting errors, tracking the locations that have exhibited errors, repairing individual bits, things like this. I think there'll be a lot of research in all these directions. And as far as whether it's worth investing in all of these mechanisms, I think absolutely yes, because it's a whole other side to what's happening here, right? These could develop themselves into cooperative solutions. They could develop into alternatives to what we use today, which could just, all of this serves to just continue DRAM scaling in a direction that we'd like to see go. Very good.
This is a new comment of the
Okay.
It's not a question, but part 108, I think, I'm pronouncing that, making a remark about XMP profiles.
Yes.
In PCs, you have the XMP profiles that allow overclocking, and they think it was pushed by a consumer called Intel.
Yes, I think that's true, right? It's part of like Intel's memory controller offering, like the XMP profile. Yeah, that's been there for quite a while. I think that's a perfect example of this, right? It's not driven by the DRAM producer, right? It's driven by a consumer. The Intel is not producing the memory chip themselves, but they enable like the user to, I guess, relatively easily configure the operating point for DRAM. And so they allow you to mess around with these timings I mentioned. And so by doing so, you could extract more performance, more energy benefits, whatever you want from your chip. So I don't think it quite counts as a cooperative solution, but I think it is like very much an example of work that pushes towards a cooperative solution. Good comment.
I guess we don't have any more questions. So unfortunately, today is the last day that Dinesh is here. Unfortunately, he's traveling tomorrow again. So I hope you had a chance to meet with him, talk about your research, get some feedback. If not, I highly recommend to do so because Dinesh has been mentoring me for all my papers, and I highly got benefits out of that. So I just wanted to remind that. And thanks for your talk, and thanks for your visit as well. Yeah, that's the end of the session, I guess. The scientist speaker.